Hi everyone, Mr. Neighbor, and we're going to talk about momentum today. So momentum is a term that was brought to life when Newton was describing moving objects. He wanted a way to talk about a quantity that involved how massive an object was, how much inertia it had with its velocity. And this quantity became known as momentum. So momentum we symbolize with a lowercase p and is equal to your mass, which is inertia, times your velocity. Because velocity is a vector quantity, that's going to make momentum a vector quantity. So the momentum of an object with no velocity has what momentum? So if I look at the momentum equation, if velocity is 0, that means this whole side is 0, which means momentum is 0. If an object with negative velocity has what momentum? Well, if velocity is negative, that means momentum is going to be negative because mass always has to be positive. The units for momentum are, well, mass's units are kilograms and velocity's units are meters per second. So these are the units we use for momentum. It doesn't have a shorthand like force does for newtons, which is kilograms per meter per second squared. This only has kilograms times meters second squared, kilograms meter per second. So let's compare some momenta. Which of these two objects has more momentum? Remember what our formula is for momentum. It is the mass times the velocity. So they have the same mass. This one has less velocity, which means the one with more velocity will have more momentum. Let's do the same thing. Let's compare momenta. Do these objects have the same momentum? So we have the same mass and we have velocities that aren't the same. This one is to the left, so maybe I classify the rightward direction as positive, making this a negative velocity. So are the two momentum the same? The two momenta? No, they're not. This one's going to have a negative momentum, where this one is going to have a positive momentum. So the sign matters. All right. What would you have to do to give the apple the same momentum as the tennis ball? So let's quickly calculate what the momentum of the tennis ball is. So we have P equals mv, which is going to be 1/10 times 5, which would be 5/10. And that would be kilogram meter per second. So what does this have to do to have the same amount of momentum? Well, it needs a velocity in this direction. If it was the same velocity, it would be less because the mass is half as much. Oops. So the velocity to compensate for half the mass has to be double. So this should have a velocity of 10 meters per second. If you want to go through the formula, you could say this momentum has to be 5/10. I know the mass is 5/10. So then what does that mean? This has to be 10. Oh, shoot. I'm sorry. I thought this was 0.0500, which would make that correct then. But right now, as it stands, this arrow, I'll do it in a different color, I'll do it in blue, should be 1/5 as long as this arrow right here. So that makes sense why I was doing that incorrect. So 1/5 of this would be 1 meter per second, which is what you need right here, not 10, but 1 in order for it to come to be 0.5. Sorry about that. I was thinking about it with this number. So that does work out. 0.5 equals 0.5 times 1, which we found. All right, next comes conservation of momentum. When we think of conservation, we are trying to keep everything. We're not trying to lose anything. We're conserving it. So when we talk about momentum, total momentum before a collision equals the total momentum after a collision. So if you have an object like a ball and it has such momentum, mass times velocity beforehand, after it collides, it's going to have the same amount of momentum. Now, that momentum might be dispersed if it's not inelastic collision, which we're not really going to talk about those much, but the momentum in total is always going to be the same if you look at every single object. If it's completely conserved within the same object, then they're going to equal the same thing. And remember, mass doesn't change, only velocity does. So whatever the initial velocity is, that's going to be what the final velocity is. But again, this might be a couple different things added together. You might have a couple objects in here for what the initial momentum is. So we'll see a couple of those. All right. 1,950 kilogram police car going 12.5 meters per second. Rear ends a 1,500 kilogram sedan moving at 3.0 meters per second. After the collision, the two cars move together as one unit. What is their final velocity? So we are first going to find the momentum of the police car. So momentum of the police car is going to be 1950. We're going to multiply that by how fast it was going, 12.5, and we're going to get out its momentum. So that's the police car. Then we're going to find the momentum of the sedan, and that is 1500, and that is going at 3 meters per second, and then get out that answer. That was the sedan. So these are my two momentum, and their labels are kilograms, meters per second. And if I want to find the total momentum at the start, the initial momentum, I have these two objects I need to add together. So that will be 28,875 kilograms, meters per second. Notice I've been putting a little underline here under my values. That's just to show where the significant figures are at this point. So right now, if I were to end the problem, I would have to round to this spot, and it would be 28900. But I'm not going to do that because I'm not done with my problem. I'm just going to keep that in the back of my head by having that little mark there. So now the final the final momentum. We know that the final has to equal the initial. So it is also going to be 28,000 approximately. I do know what the mass of both cars are. So the final momentum, which is that, is going to equal the mass of my two cars. They're going to be multiplied by whatever their combined final velocity is. So that's the one thing I don't know. So I just have to solve for that. So adding these two together, and then I'm going to divide them to the other side. When I divide, I get out the number approximately 8.36957, and that continues on. And then when I look at what my sig figs were, my sig figs took me to the 100th spot here. They were in the 100th spot here as well. So when I divide a 3-digit significant number by what this came out to be, which was a 2 significant figure number, that would leave me with 2 significant figures as my answer. So this would be rounded to 8.4 meters per second. And that's what the final velocity is when that police car and sedan are traveling together after impact.